So friends, welcome back to our YouTube channel. In today's lecture, we will talk about propositions of order of elements of group. So first of all, we will see the definition for order of element. We have seen this before, but we will just overlook it. So if we consider any group as G and we consider some element A from that group, and if there exists a positive integer n such that A raised to n is E, then the least such positive integer n is called as order of A, which is written as O of A, small o of A. If no such element n exists, then A is of infinite order. So friends, we have already seen this, we have already explained this. So we all know that if A raised to n is equal to E, then n is the order of element. So let's go next. We will see division algorithm because we will need this to prove some propositions today. So what division algorithm says, if a and b are given integers with a is not equal to 0, then there exists a unique integers q and r such that b is equal to aq plus r, where 0 is less than equal to r less than absolute value of a. If A does not divide B, then R satisfies the stronger inequality, that is 0 less than R less than absolute value of A. So we will see this with example so we can understand it. So what we are saying there, if A and B are given integers with A is not equal to 0, then we can find some integer Q and R such that B is equal to AQ plus R. Okay. So let's consider A and B as 2 and 3. Okay. So let's consider A as 3 and B as 2. So according to this definition, we can write 2 is equal to 3 into some number plus some number. And these are integers belonging to Z. So if we take Q as 2, what will give it us? It will become 6. And we can take R as minus 4, right? So as minus 4 belongs to Z, then what will we get? We will get 3 into 2 as 6 plus minus 4. Then 6 minus 4 will become 2. Hence 2 is equal to 2. Therefore for AB as 3 and 2, we find Q and R as 2 and minus 4. That they follows this equation, B is equal to AQ plus R. And this is division algorithm. This is given us in this division algorithm. And we will be using this division algorithm to prove the next proposition. So let's go to the proposition. What it says, if order of A is M and A raised to N is E, where we know that A is the element of the group and order of that element of group is M, and also A to the power N is also giving us identity, then M divide N, and we denote this as like this. M divides N, we pronounce this as like this, and we denote them as like this. Okay, so the proof is given as, suppose M does not divide M, we are considering contradiction. Hence by division algorithm, which we just see now, there exists some Q and R such that N is equal to MQ plus R, where 0 less than R less than M. Here it is satisfying the strong inequality because we are saying that M does not divides N. Okay, so since order of A is M, we have seen that order of A is M, we have considered it. So we get that A raised to M is equal to E, right? Hence A raised to MQ is also equal to E because Q is the multiple of M here. Therefore we can write as A raised to N is equal to A raised to MQ plus R from this equation, as N is equal to MQ plus R. Therefore A raised to N is equal to A raised to MQ plus R. But A raised to MQ plus R can be written like this, A raised to MQ into A raised to R. And we have just seen here that A raised to MQ is identity. Therefore we will substitute this value of A raised to MQ here, which is identity, that is E. Therefore E into A raised to R. But E into A raised to R is nothing but just A raised to R. So finally what we get a raised to n is equal to a raised to r from this result. Okay, this result star, we get a raised to n is equal to a raised to r. But we know that a raised to n is e, and this is given here in the proposition. We are considering that order of a is m and a raised to n is e. Therefore a raised to n is e implies that a raised to r is e. Therefore a raised to n is equal to a raised to r is equal to e. But this is contradiction. This is contradicting the minimality of m. Hence it is not true that m does not divide n. Hence m divides n. Okay, this is our proof of first proposition. Let's go to the next proposition is, if G is a finite group, then order of every element of G is finite. It is very simple proof actually, and we can consider it as, if G is a finite group, then order of every element of G is finite. We are considering G as a finite group of order n. Okay, and a be element of G, we are considering some arbitrary element a from that group. Then we are considering the elements a square, a cube, a raised to n up to a raised to n plus 1, and these all will be the elements of G because a is the element of the group. As a is the element of group, therefore these all will also be elements of the same group, as these are the powers of a. But G has exactly n elements. We have said that G is a finite group, then order of every element of G is finite. We have considered here its order is n. Therefore the group G has exactly n elements. Hence two of these elements must be equal, because we are saying that the elements a square, a cube, a raised to n, a raised to n plus 1, these all are elements of the group, but group have just n elements, not a raised to n plus 1 element. Therefore two of these elements must be same to get n elements in the group. Okay, and we are considering them as a raised to p and a raised to q. So we may assume that p is greater than q, right? A raised to p and a raised to q are two elements that may be same, and we are assuming that p is greater than q. Hence a raised to p minus q will be identity, as p is greater than q. And how this come? So let's see. So we are saying that a raised to p is equal to a raised to q. If we divide both sides by a raised to q, it will give us a raised to p upon a raised to q, which will be equal to identity, and a raised to p upon a raised to q, this can be written as a raised to p minus q, which is equal to identity. And the same thing we are saying here, that a raised to p minus q is identity. Hence a is of finite order, as p is positive and q is less than it. Therefore a raised to p minus q is identity. Therefore this implies that a is of finite order. Therefore every element is of finite order. As a is of finite order, therefore a raised to 1 must be of finite order, a raised to 2 must be of finite order, a raised to n must be of finite order. Therefore every element of the set is of finite order, and this is proved. But the converse of this proposition is not true. That is, if order of every element of group is finite, then G is finite group. This is not possible. Let's see why so. All roots of unity under multiplication. This is the example, which is exception, which is a contradictional example. Every element has finite order, but every order of group is infinite. Let's see. Consider the roots of unity, which are 1 and minus 1. Okay. So order of 1 is 1 and order of minus 1 is 2. Okay, we know that. Then consider the fourth roots of unity, that is 1 minus 1 I minus I. In this case also we know that order of 1 is 1, order of minus 1 is 2, order of I is 4, and all those things. But the order of groups, roots of unity, is infinite, because there are infinite numbers of roots of unity. Okay, so this is the counter example. So converse is not true. The next proposition is, if order of A is m, then order of A inverse is also m. And its proof is given as, we all know that A into A inverse is equal to A inverse into A, which is equal to identity. This is the existence of inverse. Okay. Hence, we can write as A into A inverse bracket raised to M. We have taken its mth power, and this can be written as A's mth power into N inverse mth power. Therefore, A raised to M into A inverse raised to M, which is equal to E. Because we know that A into A inverse is identity, and here is same thing, just we have raised both of those to the mth power. So this can be seen as A raised to M, and this can be seen as A raised to minus M. Therefore those both are inverses of each other, therefore their multiplication is again identity. Therefore A raised to M into A raised to minus 1 raised to M is identity. Then this again implies that A raised to minus 1 raised to M is E. Order of A is M. Therefore, A raised to M is identity already. Therefore, A raised to minus 1 raised to M is also identity. Again, order of A inverse divides M. In other words, order of A inverse divides order of A. This shows us that order of A inverse divides order of A, and we can similarly show that order of A also divides order of A inverse. Since both are positive integers, we get order of A is equal to order of A inverse. Okay, so this was our third proposition. So what we saw today propositions of order of elements of a group. In that we revise the definition of order of element, then we see division algorithm, then we see the proposition that is if order of A is M and A raised to N is E, then M divides N. Then again we see that if G is a finite group, then order of every element of group is finite. And we said that converse is not true, and the counter example is all roots of unity under multiplication operation. Then we see the next proposition as if order of A is M, then order of A inverse is also M. So we will stop here for today. So please do like, share and watch our videos. Thank you.